Good morning, and it's my pleasure as the director of the Wolfgang Pauli Institute to introduce our Pauli Fellow. Burkard Hillebrands is here not for the first time in Vienna. And our role as Pauli Institute is to be at the service of the scientists in different faculties. So since this is a talk mainly designed for physicists, I come here to the Faculty of Physics, being a mathematician and physicist myself, very interested in the topic. And so I think the best person to introduce Burkard is André.
Thank you very much, Norbert. Thank you, Burkard, that you found time to visit us with this nice stay here for discussing science and for giving us a lecture. So, as you might know, I know Burkard very well. Since I built, he took a decisive role probably in my academic career. I spent in Kaiserslautern time from 2007 to 2019, so 12 years in the group of Burkard Hillebrands, and started as a postdoc and finished as an assistant prof before coming to Vienna. Yeah, so I'm very grateful for your support. And so now Burkard Hillebrands is a professor emeritus of experimental physics at the Rheinland-Pfalz University of Technology. There was a rebranding. In my times, it was University of Kaiserslautern, of Technology, Kaiserslautern. Now it's a little bit broader, so more cities involved. He, after studies at University of Köln and postdoctoral studies Optical Science Center in Tucson, Arizona, he became associate professor of University of Karlsruhe, so this famous KIT, in 1994. And since 1995, so it was a very quick career, he got a full professor at the University of Kaiserslautern. So Burkard was very much, so he, in terms of scientific, he has more than 430 referred articles, book contribution, patents, and so on. So he's super successful, very well known in Germany and in the world. But he was also very active, involved in administration of science and in supporting. For example, he was a vice president of Research and Technology and Innovation of University of Kaiserslautern from 2006 to 2014. And he was a scientific director of Leibniz Institute for Solid State and Material Research in Dresden from 2016 to 17. And there is a very, very long list of awards of Burkard Hillebrands, so maybe I will name only some of them. So he was in 1922 president of European Magnetism Association. In 1517, he was chair of International Union of Pure and Applied Physics. He is fellow of IEEE, of APS, of Institute of Physics London. Burkard Hillebrands received...
Pauli, don't forget Pauli.
And now Pauli Institute, yeah. You're right. And in 2016, Burkard Hillebrands had an ERC advanced grant and performed studies of Bose-Einstein condensation of magnons. That's what we will hear, lecture today. And let's say you have all this file, you can read more and more awards. So Burkard, it's a great pleasure. Thank you very much that you have found time to visit us. And yeah, thank you for your lecture, and looking forward.
Good. Thank you very much, André. It's a big pleasure for me to be here again. And you can really believe me, I'm not coming here as a duty. I'm coming here for two reasons. Number one is excellent science you do here. And number two is, of course, to meet friends. And I think science lives so much from personal connections. And I think André and I, that still André invites me after working 12 years with me. I think that is a very good sign of friendship, isn't it, André? Yeah. Good. So I now have a very difficult task to do, which I do very, very seldom in my life. And that is to give a basic lecture of magnonics, which is not a difficult thing to do. I've done it very often, but the difficult part now is to give it to an audience where a lot of Brillouin light scattering, magnonics, and so on is already done. And I was urged to do it on a level that everybody can understand it. It should be much wider than only your own group. So I'm trying my very best to do this. André was already mentioning that I am now Professor Emeritus, we call it. Actually, I'm elevated. I'm now elevated to senior professor, which sounds much better than regular professor. I don't tell you the difference in salary because that is nothing to laugh about. Yeah, it's okay. But what I'm doing actually is I'm trying to use the free time I now have for a couple of new things. One is to really think about where will our community go? So what is the future behind? What is the potential we have from a somewhat more outside view? And that is where we can have a lot of discussions. And I also started to do something else, which I'm advertising here on this view graph. That is, there is a very critical community within our community, and that is a community of the junior professors or Eminöter stipends in Germany, or freshly employed professors. And what I'm now doing is advising these things. I do it on three different, no, it should be done on three different paths. One path is that you do coaching, but coaching can only be done by a professional person who has a training in psychology and so on. I cannot do this. And there is mentoring, and mentoring again needs two stages. Mentoring stage number one is to tell you what do you have to do as a young professor. Yeah, what kind of duties will come to you which you have never thought about. And number three is of course to have another mentor or other mentors which will go with you through your scientific life, which will tell you, oh, Andre, this is not a good idea what you are doing here. Don't waste your time on this proposal. Better write the other proposal. Yeah, and I mean, if we are very honest to ourselves, no, but I'm asking you now. We always have made a mistake, and we would have been thankful if other people would just help us. So this kind of mentoring, of course, I cannot do, but I can tell you all the tricks and twizzles, how to become a young professor and how to have a successful career. The things, very simple things, excellence versus reputation. Of course, is University of Vienna an excellence university? That is an answer, a question you always have to answer. Yeah, if you think about it, who is excellent? Maybe Nobel Prize winners. Yeah, but is an ERC grantee excellent? Maybe he was only lucky in the selection process. Yeah, you can doubt it because you didn't get the prize. Yeah, and this colleague got one, so is he more excellent than you? I'm very sure. You will have nice discussions about it. Yep. Okay, so that is a big thing. So excellence is nothing you can compare, but you can compare reputation. And if you accept that you can compare reputation, I mean, how do you do it? Very simple. You agree on the measure. The measure can be number of invited talks. The measure can be number of joint papers with Nobel Prize winners. The measure can simply be the H factor or the M factor or tell me anything else. And once you agree, you can compare. And then I can tell you, okay, for instance, I'm much better than Andre because I am always favoring the H factor. And since I'm just older than Andre, I will always win. Very simple. Yeah? But Andre might be clever. He might simply say, oh no, H factor is not good. Let's take the M factor. M factor is citations divided by the years after the PhD. Maybe he's much better than me. I didn't calculate it. Yeah. So you see, it's very important to choose the right measure. But I think you understand. And why I'm teaching this to you, very simple, because if you accept this, then you can optimize. You can develop a strategy. How do you optimize your reputation? What should you do? What do you better not do because you are wasting time and so on. So I'm advertising this. And I do it usually in a one-to-one meeting that I meet a person for 2 hours, 2.5 hours, and then it can be done. I'm offering this to you. I'm here the entire week. So those of you who are really interested, and that is starting on the senior postdoc level where you might start to think about a scientific career as a professor, or if you are a freshly employed person, then I'm very happy to do this. I am also doing it from time to senior people, like Andre, or maybe you know it if you're interested in time, because these people I like to use as multiplicators, yeah, just to spread the ideas and to tell their own people what is important here and to teach them. Okay, so much regarding this advertisement. You see the items, you have to understand that you should actively manage many things. You should develop a career strategy. Think about the secrets of comfort zones. It's very, very interesting how many excellent people you find around, but which are working on topics which are absolutely boring. Yeah? I mean, obviously, these people have done something wrong. And of course, very important is just to better understand how to guide a scientific group if you are just in the process to develop your skills in this field. So now we have to do our work. let's start with what we do. And number one is, of course, always the people we have contributed here to the talk. You find here a lot of PhD students, or actually people who just have finished, like Matthias Schweitzer. You find people like Vitaly Vasushka, a good friend of Andrei, Matthias Weiler, who is now my successor, Georg von Freimann, who is another colleague. You might know Alexander Saga, Philippe Perrault in my group, and we have many collaborators. I'm only listing here a very few ones. And of course, one of them is Andrei, very clearly. So, key idea of magnonics, you know, this is a spin, you know, all about a mechanical spin. You know that the spin in the field of gravity is just having here this kind of precession. If you have many of them, they can be coupled. And if you have coupling provides coherency. And you see that all these spins here are actually now precessing here very nicely with a very well-defined phase relation between them. You can actually analyze these pictures, and you find waves which are propagating, and that is what we are discussing here. Now, not with the mechanical spins, but with the spins you have in a ferromagnetic or ferrimagnetic medium, where you have coupling via the exchange interaction as well as by the dipole-dipole interaction, and this you can study. And in a nutshell, what can you do with this? Of course, you can already right from the beginning think about potential applications. I'm really carrying oaths to Athens here, because you just have to listen what Andrei is doing. Wave-based computing is interesting, wave guiding, coherence, interference. And then it comes to the specific advantages from which we are making really our living, because magnonics in many respects is so much better than other communities, because we have built-in coherency, so we can do interference experiments, and we have built-in nonlinearity already in the equation of motion. So anything which depends on elastic waves or on electromagnetic waves, you don't have this disadvantage. Electromagnetic waves, Maxwell equations, I hope you all can remember the Maxwell equations. Yeah, they are linear, so you have superposition of waves, but no nonlinearity. And if you dare to have nonlinearity, you have to play very complicated tricks. You have to use nonlinear optic materials and so on. So this becomes material properties. Here we have it for free. It's all in our own world, and we can already use it. Scalability, we can make these waves very, very small, much better than optics. I'm always fighting optics, you know this, yeah? You can make the waves as small as interatomic distances if you like. So scalability is given. And then there is something else I find very, very important. I told you I'm now trying to think, where could magnonics be in the next, not 10 years, that is what Andrei is doing, in the next 20 years. Yeah? And that is a difficult question, a very difficult question. Of course, you cannot foresee the future. But if it comes to science politics, yeah, there is a very difficult question, because if you define an aim which is 20 years from now, you cannot ask for funding now to achieve that aim 20 years ahead, because funding is always for 3 years or maybe 6 years. But sorry?
Fusion and quantum computer, they can.
Yeah, because they have something we would like to have, and that is a long-term strategy. Yeah, and you are exactly giving the answer what I wanted to say. We have to develop a long-term strategy. But if we want to develop a long-term strategy, we have to say why. Fusion is simple because we have an energy problem. Quantum computing is simple for 2 reasons. Number one, we want to have better computing capabilities. And number 2, we want to have something for our heart. And quantum sounds so strange compared to classical physics that we always like to have something very strange. So quantum mechanics, which nobody understands, pushing it to the limits that we have, that billions of dollars or euros will go into it, is of course something very appealing. That moves the heart. Yeah, you have to move hearts if you want to get really big things to be done. But here is an example which you all understand. Think. And if you think, what are you doing? Yeah, you are moving little potentials, chemical potentials, and so on in your brain. And your brain is 3-dimensional. Why is your brain 3-dimensional? You can give the answer because we have an evolution process in biology, blah, blah, blah. Yeah? But the real reason is, in order to make your brain functioning, you have neurons, which are, so to speak, your mini computers. You have many of them, and you have connected them. And between each pair of neurons, Yeah, sorry, for each neuron, you have 10,000 connection lines to the other neurons. And now I'm asking you, show me how to do it in a two-dimensional world. Show me how to do it in a two-dimensional world, such as silicon. And you will find out, yes, you can't do it. Yeah, I mean, if you look into the silicon world, there's a highly developed technology, but they are really coming to the limits. They are always overcoming the limits somehow, but you can imagine to do it for another 20 or 30 years, that is probably not possible. So one has to search for alternatives. I don't know what the alternative will be, but I'm convinced that magnonics is a very potential candidate for that. And that is why I put a long-term strategy into magnonics. And that is why I'm advertising it all around the world, because we have to build a community. It's not only for the own lab. We are a big community. We all together have to move it forward. So that is what I have in mind. I think three-dimensional computing with magnonics is something you can understand. Good. This picture I took from a publication with Xi Wang, who was here for a long time, and Andre have made. I mean, you cannot understand. It's a very, very complicated, very busy thing. It tells you what you can do with magnons, and the field of magnons is called, of course, magnonics. Just read the word outside. You can control, so you can control propagation. You can look into excitations. You can manipulate things very nicely, very sophisticated ways. And so you have all the ingredients you need for data processing or signal processing. I'm using here in my talk the word data processing and signal processing, somewhat synonymous, oh, difficult word. But please understand, these are different fields. Yeah, I mean, data processing with magnonics is probably not very likely to develop extremely good in the future, but signal processing will, very certainly. Yeah, good. I didn't bring you the classic example you could see with the last Nobel Prize, where a quantum computer is shown. And these quantum computer pictures, you all have seen many of them. They always look extremely busy. Do you know why they look so busy? Did you ever notice this? The quantum chip is this small, yeah? But there's a huge thing around. And then you tell, well, we have to do it at millikelvin temperatures and so on and so on. But if you look, the thing is extremely busy, because in order to match the noise problem, yeah, you have not thousands, but nearly 1,000 directional couplers in it, where microwaves can only go in one direction through, but not in the opposite. And this is all classical hardware. One device for each bit. Yeah, and if you want to have 100-bit quantum computing, you have already 200 of these devices, because you have to bring the signal in and the signal out. You have to reduce the noise. So these look so big. Magnonics helps. We have a European project, which actually, Philip, and I think you're also involved, where this can be miniaturized. At the very end, quantum computers will look much more boring. They still have the little chip, a quantum chip, plus another chip with all the directional couplers, and everything is smaller. Good. So applications, I was already mentioning wave-based information processing, and of course, very much unconventional computing, such as neuromorphic computing, which is becoming more and more important. Very soon, it will not be unconventional computer anymore, because you know, you all have your ChatGPT, and we need a magnonic version of ChatGPT, of course. But I think that is not so far away. This can be done. Yeah. So what I'm going to talk about is a lot of things. I cannot cover this all in this remaining 1 hour time or so. I would simply suggest we move forward, read it. If you pick an item which is extremely interesting to you, we can address that. Let's do it in an interactive way, because I should not be the only person who is talking. Tell me what you are interested in, and then we will do it. So the recipe is simply, I will talk about a little bit the basics, which I did. I will talk about Bose-Einstein condensation, Magnon BEC creation and detection, and then I will address a very fundamental problem, that is the coherency of a Bose-Einstein condensate. Then I will show you there are several ways how to make Bose-Einstein condensates, magnonic Bose-Einstein condensate, and that we can control it very nicely. And this brings us to the point that you will see that Bose-Einstein condensates might be fantastic objects. Just to tell you the most important secret about Bose-Einstein condensates, number one, you describe them with macroscopic wave functions. Yeah, this should echo what you just have learned about the last Nobel Prize this year. I will show you a view graph on that. That is about creating macroscopic wave functions. We have it in magnonics, and we always get two of them. So we have two wave functions which can interfere. And now if you are a little bit in this field, you know we have the recipes for making qubits, so we can make magnonic qubits. And then, of course, you have a wonderful starting point to develop other things. Good, so that is what is going on. Applications of that, for instance, how to do qubit calculus, I will do in the second lecture, which I think is tomorrow, just to advertise the second lecture. So the basics, well, we have seen a lot. I have to show you how it works. We have a magnetic moment here in red. We have a field here in blue, magnetic field. And we excite with some microwave source whatsoever. And then we get the phenomenon of precession. You see the precessing spin here, or magnetic moment. And if we have coupling here in between, you see we get a coherent excitation of the entire body. And from this animation, you can already see that a wave is formed in this particular case, which propagates here in this direction. What you need to do, you need to describe it mathematically. And the fundamental equation is not a force equation like you have in classics, in classical mechanics. It's just a torque equation. And torques you always get if you take the time derivative of magnetization. And torque you also get if you make the cross product of the magnetization M with an external field. Yeah, you know, I don't know how you greet each other in your lab, Andre. Do you also do it like this? Yeah, yeah. That is the greeting of two magnonics people. Yeah. It's very simple because you always have at least three different directions here. Let's call this here the surface normal. Let's call this here the wave vector. Let's call this here the magnetic field. Yeah, and then of course you want to know in which direction is the magnetic moment moving around. Yeah, and with this you always can find out. Okay, because you have the cross products here. Yeah, the cross product of M and B is always perpendicular of both M and B, and you see it here if you have to sit down by yourself to work it out. If you haven't already done it, I guess most of you have done it. So if you have the magnetization here, if it is tilted at a certain moment of time, then the cross product of M and the acting field B effective goes here in this green direction. So that is here this term, and this will result in the precessional motion. You also can get some damping if you look farther about it. The most simple way how to describe a damping is written here, just the cross product between the magnetization and the change in time. Change in time is here, this green arrow, so it is just this arrow here. And it just depends on the sign, whether the process is enhanced or usually it is just damping. So you get the damping. That is the most natural way, and phenomenological parameter which describes the strength of the damping process. So that is basically the starting point. You put it on any simulation software, and then you can simulate the stuff. It is not cheap because it's a multi-dimensional problem. So, but the experts are more than you know how to deal with it, and then things can be done. A very important parameter is the wavelengths. You see here the wavelengths because these wavefronts here have the same phase, and correspondingly. You can always attribute here a wave vector k, and then we are in the field of discussion of dispersion properties. So how does the frequency change with the wave vector? And you might notice already a very important property, the wave vector k, yeah, points in a certain direction, and the frequency depends on the direction. So it's not an isotropic problem usually. Yeah, in very seldom cases it is isotropic. And what makes our life richer, I don't like to talk about difficulties, I always like to talk about richness. That is a wonderful fact that we have two interactions. One is exchange in energy, yeah, which just comes from twisting neighboring moments because of the quantum mechanical overlap of the wave functions. The overlap changes, and therefore the exchange energy changes if we tilt two magnetic moments or two spins against each other. And the other is a dipole energy, simply what you know from your fridge magnets. Yeah, you can keep them separately over macroscopic distances, and you still feel a force between them. So that is a dipole energy. And if you have now precessing moments like you see here, just see this moment. If you take a snapshot in time, has a component pointing up, This one has a component pointing down. So these are two little dipoles, and of course they generate a dipolar field, which is just indicated here with these dashed blue lines. So we have little magnets moving around, if you like to look at it in this sense. And then it is immediately clear to you, if you have little moving magnets, we have another energy contribution. You can immediately guess the distance laws behind how does it behave. Exchange energy is always very, very short distance stuff because you have overlap of wave functions. And dipole energy, go to your fridge at home if you can't remember, and you notice you have this over large distances, yeah, well, much larger distances. So this makes our life rich because if we look into phenomena where the distance plays an important role, you have a transition between these two interactions. And this is another classical picture. What you see, we now take a big step forward. We take the Landau-Lifshitz equation, we put it on a computer, or we give it to a colleague who can calculate it analytically, and then we get the dispersion of the spin waves. And don't feel too much worried about that this looks like a very complicated picture. All you have to take out is, number one, we have dispersion. Dispersion is we have a frequency dependence of all of these modes. These modes have different names. And what is different is always the propagation direction. So here's the propagation direction is here horizontal, but the field points to the back. Here the field points perpendicular to your sample, and here the field points parallel to the wave vector. There are different geometries. This one, again, yeah, in one case, two of these vectors, like here, this was too fast. Two of these vectors point here in the same direction. Yeah, you get it? And what you see is the dispersion is very funny. Normally you assume if you have a larger wave vector, think about light, yeah, the frequency will increase. And one mode here shows this, is actually called the magnetostatic surface spin wave, but this is only a detail. Or here, this mode, if the field is perpendicular, the field increases very nicely. But here is a very strange mode, which you see here, which decreases here the frequency. Number one, just phenomenological. The group velocity in these kinds of diagram, go wherever you like to go. You go to electronic band structure, go to phonons. The group velocity is always a slope. And you notice the slope is negative, so we have a negative group velocity. So if this is a wave vector, yeah, if this is a wave vector, the mode will move in this direction. Energy transport is here, opposite direction. Very strange, but very useful. Yeah. So for that, we call this a backward volume mode. I will use this name a little bit. That is only for dipole interaction, but you can also include the exchange interactions, and everything becomes a little bit more complicated. But don't feel worried. You still can see here the surface mode, or here's a backward volume mode, negative slope, or here the forward volume mode where the field is perpendicular to the sample. And what you see for larger wave vectors, all these modes move on because here the exchange interaction sets in, and ultimately it will be proportional to the wave vector squared, which you find from very simple analytical investigations. And to make it even a little bit more complicated, no, more rich for you, just have a look. You see always here many, many modes. Yeah? Why is that? That is very simple because in the lab we don't have huge bulk samples. We very often have films. And if you have a film, we get standing waves which travel forth and back between the back side and the front side. They form nodes, 0 nodes, 1 node, 2 nodes. You see it here, 3 nodes. So we get all these standing waves in addition to the propagating part. So these modes usually have a propagating part and a standing part in a 3-dimensional material. And all these standing modes are indicated here by the thin lines that you see here over. So take-home message, it is not complicated, it is very rich. And we have many ways now to utilize it, and people like André Weigel living with their group to investigate all these properties and to take all the potential which lies in this rich phenomenon. So let me now, is this fine? Is this okay? That was a very fundamental part. Now let's make it a little bit richer. You have seen this animation here, the spin waves. And now what we can do, we always win if we change the angle of view on a certain topic. Yeah, we have seen classical physics. This was all classical physics with a little sort of grain of quantum mechanics. We had exchange interaction, but everything was macroscopic. So we have the spin waves here, but now what we can do, let's change it, and let's not think about waves, let's think about particles. So we use the wave-particle duality. Yeah? Particle is called a magnon. What should a magnon be? Very simple. We can calculate the energy that is in the exchange limit, goes with a linear momentum squared. We can calculate the linear momentum because h bar times the wave vector q. Wave vector is sometimes k, sometimes q. Don't worry, that is you for both. You can assign a mass, same as electron mass, you know, heavy fermions and all the other strange stuff. Yeah, where heaviness comes into the game because of anomalies in the electronic dispersion. Yeah, you take the curvature, the reciprocal value of the curvature in a dispersion is a mass. Yeah. So you can make particles very heavy if you have some very little curvature. Same here. So we can assign a mass to our magnons. Also, there's no real mass moved around. It's just effective mass. And now really quantum mechanics comes in as a spin. A magnon has a spin 1. Yeah, with a spin 1, a boson particle. And what we also have is scattering processes. I told you Landau-Lifshitz equation is so nice because it's intrinsically nonlinear. Now we have to translate this sentence, it's intrinsically nonlinear, into our particle world. Yeah? What does it mean? It simply means particles travel around like a soccer ball. Yeah? Particles interact. We don't usually have two soccer balls, but I think you can imagine what happens. So they can just meet, they can scatter, so two balls are meeting here, and then they go in two different directions. That is a 4-particle scattering event because 2 particles are coming in. It takes a snapshot of interaction, and 2 particles are coming out. Are you good in first and second year fundamentals of physics courses? Then you are very familiar with this because that is how you learn classical thermodynamics. Yeah? How does thermodynamics happen? You have a finite temperature, so all your particles have kinetic energy. Particles are now the molecules in the air because we live at 300 Kelvin and not at 0 Kelvin. And these particles move around and they scatter. And you get the classical thermodynamics simply by considering the kinetic energy of these things and the exchange mechanism, scattering processes. 2 gas molecules meeting, and then you get the scatter. Under energy and momentum conservation, that is very important. So the same thing we have here. So we can look into the scattering processes. Linear process is boring. You just have a particle, and here is some distortion in your material. Material is not perfect, so it gets scattered. You know this from phonons, or you know this from optics. If you have dirt on the window, yeah, you know this photons from the sun are scattered, and suddenly you see something. That is just 2-particle scattering. 2-particle because you have an incoming particle and an outgoing particle. That is how we count the particles. Then we can have the nonlinear processes, 3 magnon scattering. So 1 particle is coming in, and then the particle decides to split into 2 other magnons. Yeah, that is possible. And always, if you have quantum mechanics, the good thing about quantum mechanics is quantum mechanics is usually time reciprocal. Yeah, you can also think about the opposite process. You have 2 particles coming in, they merge, and only 1 particle is coming out. And of course, the laws of physics must be obeyed. So you have energy conservation, you have momentum conservation in these processes. This simply means that if you have this green magnon particle and you have this process that these blue magnon particles usually have something like half the energy or half the frequency of the green magnon. And the opposite thing, you can have 2 green magnons and then they combine to a blue magnon. This can happen. And then you can continue 4 magnon scattering. That is actually something we just discussed in terms of classical thermodynamics. 2 particles are coming in and they are scattered. Momentum is conserved, energy is conserved. So this really makes a full correspondence to classical thermodynamics of our air system, yeah, of classical temperature. So, well, now what we can do, we have clever people in our community and they tell us, oh, we have this fantastic dispersion where the modes move around and sometimes they go down and then they go up and form minima. So we have areas in the spectrum where we have magnons and we have other areas in the spectrum where we don't have magnons. Yeah, you have seen it, you might remember. Yeah? So if we make it in a way that this process with the 3 magnon scattering has residual magnons which are in an area where no magnons are allowed, then you suppress the scattering process. And then you end up here with 4 magnon scattering processes only, and this works. And now Bose-Einstein condensation. Well, Bose-Einstein condensation, you all know the Bose-Einstein distribution function is just the denominator here. Yeah? So an energy term divided by temperature, you take the exponent of that -1, and then you get the Bose-Einstein distribution function. If you multiply it with the density of available states, and that is d as a function of omega, you get the density of occupied states, that is rho as a function of omega. Fundamental physics, yeah, just with them. And magnons are bosons, so this formula is applicable. But we can do in a practical world, we can add a chemical potential here. Chemical potential is something very tricky. I'm not so deep in, I don't want to go so deep here in thermodynamics. But a chemical potential is a fantastic parameter to describe something you don't want. You want to live in a linear world, in a ground state world. So if you disturb the ground state, and if you do it only gently, yeah, the deviation from the ground state world you can describe with this chemical potential. And this works very well in the discussion we do. What you can do, you can take this formula here and plot it, so we plot the quasi-particle density as a function of the frequency, and we throw in here the dispersion. You just have seen the very simple dispersion. Yeah, and we do a log-log plot for simplicity. And we do it for the backward volume mode. You might remember the one with the minimum we had, yeah? Backward because initially the slope is negative. Yeah? Then we get already a minimum frequency, which is here. And at t equals 0 and 0 chemical potential, the curve would look like this. It's just putting everything on the computer, very simple. So now what we can do, of course, we can disturb the system. For instance, we have a knob, and we can turn the knob, and we can make the chemical potential equal to the minimum frequency, okay? Let's just assume that. Yep. Then what we can do, we can look at the formula, what happens here. Now we have h bar omega minus the chemical potential. In this case, if it is equal, so the denominator is 0. We have the exponential term of the exponent of 0 is unity. And then you find another unity here. Unity minus unity again is 0. So you have a 0 in the denominator, which means this function will diverge. And you see it here exactly in the log-log plot, how it diverges here at exactly the omega min frequency. And that is where we are experimentalists. We tell the theoreticians, well, thank you very much. That is so nice that you show this to us. Now we will go to our lab and we will realize it. Can we really place as many particles as possible here in this diverging density here? And in fact, that is possible. And we have shown it, what is it, 2006 actually, we published the first paper about that. And that this is indeed possible. Yeah. And I will now show you how this happens. If you talk about, I was advertising my coaching, mentoring stuff. This paper is a very, very interesting one because it is now a highly cited paper. But if you look over the years at the beginning, there were nearly no citations. Yeah, it really took time until it diffused into the community, and then it is still then constantly growing. Have a look. This is very interesting phenomenon. So now Bose-Einstein condensation. So the idea is that we treat our bosons of the magnons as an ideal gas. So we use all we know. We don't have to develop something new. We take the statistical distribution of bosons. Is this factor, again, you see the exponential function here, energy divided by Boltzmann times T, minus the famous 1 here. And so the distribution, the occupation number is just giving by taking the density of available states, dividing by this denominator, and then you get it. If you like to know the particle density of a gas of non-interacting bosons, then you have to integrate over all states. Here, this is from the original work of Einstein, 1925. So 100 years ago, we are celebrating still this kind of things. He has taken just the kinetic energy, and therefore here, the number of states is just the square root of the kinetic energy. I think that is something you're familiar with. Then you can easily understand this equation. So that is the starting point. And what happens here, in fact, at high temperatures, all these particles, or in our case, the magnons, are independent particles. They move around. Yeah. If we make the temperature now a little bit lower, then suddenly these particles, I'm now using strange words, so please excuse me. I was told this should be for the general public. Then these particles gain wave character. Yeah. And we call the waves the de Broglie wave. Yeah? And here you see the little de Broglie waves. That is only to imagine it. Yeah? But you see these waves are not yet interacting. But if you allow the waves to interact because you make the temperature lower, and so the de Broglie wavelength and also the coherency length, which is not discussed here, becomes larger, then you see it starts to interfere here constructively. And at the very end, if you have a condensate, the condensate is a single coherent, 100% coherent wave function. And if you think about the transition of Bose-Einstein condensation, it's just that. Yeah. All the parameter is coherency, very important. Yeah, you form the condensate, a coherent macroscopic wave functions out of an incoherent environment, because even here the de Broglie particles are still incoherent at this temperature. So that is, I think, a very, very important thing. So we have macroscopic wave functions, and then we can go to Andre's lab again, and we can do something good with it and do calculus or whatever. Yeah. Yeah. Initially, you know, there was a Nobel Prize for that. Initially, it was a very, very hard experiment, because what you can do, you can take the density here, the particle densities of whatever it is, take just an atomic gas, and you have to calculate the temperature at which this condensation could happen. So 170 nanokelvin, that is so low, yeah, that is hard to reach. But it was possible. Nobel Prize 2001 by Cornell, Catalan, and Wieman. They found the first thing, they call it the coldest matter in the universe. And that is their experimental observation. And you see how here in the two-dimensional velocity distribution, suddenly if you lower the temperature, a sharp peak shoots out as an indication of such a coherent state. That is 24 years ago. Okay, but there is a problem with it. There is somehow a dead end, because in order to make these kind of condensates, you have to use these nanokelvin temperatures. But if you look into it, the temperature itself, you can derive an easy expression. It's just this one here. And the essential parameter, apart from constants, is that the temperature is proportional to the number of particles divided by the volume to a certain exponent, which is close to 1, is 2/3 actually. Yeah? And this simply means you can rise the temperature if you have enough particles at hand. And that is where we kicked in. We saw, well, in our system, magnonics, yeah, is such a nice system, but we have the potential to increase the number of particles very, very much. So, and then we were successful in showing that indeed even at room temperature, Bose-Einstein condensation can happen. And Einstein actually wrote it already 100 years ago. But what happens now if I let the density of the substance grow even more at its temperature? I claim that in this case, the number of molecules which grows with the total density transfers into the first quantum state. And that is what we now call the Bose-Einstein condensate. 100 years ago, Einstein has foreseen it. Yeah? And for 24 years, the first experiments at nanokelvin were done. And then 10 years ago, we showed it. Yeah? Okay. We talk here about Bose-Einstein condensation, not of particles, not of electrons or atoms, but of quasi-particles. And here I must tell you the essential difference. What is the difference between a quasi-particle and a particle? I mean, quantum mechanics is so generous to us. Quantum mechanics allows us to discuss everything in terms of waves, the Broglie waves. Yeah? We can have a Norbert Mauser, the Broglie wave, because we know exactly the recipe how to transform Norbert into a macroscopic wave function. Yeah, I hope it is still coherent, but that is something you need to solve personally. Yeah. Okay, so everything can be transferred and then we have interference in a department. You very often have a lot of interferences, but I will not dwell more deeply about it, but I think you get the idea. Yeah, so you can make it. Yeah. Okay, but it is, of course, always a quasi-particle, and a quasi-particle has a big disadvantage that it might only live for a certain while. We all will die one day, so also the Norbert Mauser quasi-particle will only exist for a finite life, hopefully for another 50 years, but we have to see. And the same happens, unfortunately, with the magnons. Magnons are excitation of the magnetic systems, and therefore they are quasi-particles. They don't live forever. So we have to do our experiments within the finite lifetime of these particles. But the good thing is, since the number n is not conserved, yeah, we can change it in both ways. We have damping, or we have mechanisms to enhance it. And if you have thermodynamic equilibrium, the chemical potential is always zero because of this finite lifetime. So what we need to do is to increase now the quasi-particle density in order to trigger condensation. This has been done by now in many, many systems. We are talking a very fundamental process. Photon Bose-Einstein condensation has been shown. Yet you just have to have here a cavity. You have to put in a dye in order to get the necessary nonlinearity. Very complicated experiments 15 years ago. And then you can see a Bose-Einstein condensate. Exciton, polariton, BEC has been found 11 years ago in a quantum well system. So very complicated, but it works. And I will show you that it can be comparatively easily done with magnons. So let me show you how we do it. We all work with the best material in the world, that is yttrium iron garnet, which you have a lot here in Vienna. It looks very complicated, but in fact it's a perfect crystal, and it gets even more perfect with increasing time. I know that some people here have contacts to Lviv in the Ukraine. There is a best company which makes these materials, and they're really perfect. It's fantastic. So we can work with that. It has a lifetime of 700 nanoseconds, which is good enough to do a lot of good things. It's short, of course, so we usually do experiments in a repetitive way, but we can work very well with it. Yeah. And I think the record here belongs to Vienna. That is Rostislav. You have the world record at the moment. Is it still the case? Yeah. So his magnons live 18 microseconds, which is really fantastic long, but unfortunately only in the fridge. Yeah, good. Okay. So it has been observed many times, and we skip this. So we have a problem. We have to manipulate the density of states. And what I would like to tell you here is, don't worry. There are many ways how to change, how to modify the density of states. For instance, there is a process called parametric pumping. You have seen this picture here before. You just remember here the T and chemical potential equals zero curve if you plot the quasi-particle density as a function of the frequency, actually in a log-log plot. Yeah? But what we can do, we can throw additional magnons in the system via a parametric pumping process, and then you enhance here the density, and Bose-Einstein condensation can set in. How this is done, I will tell you next few graphs. But I would like to mention there are other very interesting ways. For instance, one where also you, Andre, were part of it in the story. You can play very simple tricks, and the most simple tricks is this here is a piece of yig. Yeah, you agree? Yeah. I heat it up a little bit, let's say 100 degrees, so that the iPhone is not breaking. Yeah, I have many magnons in it according to the thermal distribution. Yeah, energy K-Boltzmann times T plus 100 degrees is in here inside. Yeah, and then I let it cool down very rapidly, so fast that the magnons cannot reorient themselves. Yeah? So basically the cooling time is shorter than the magnon lifetime. And what will happen in this case, at the end of the cooling process, there are too many magnons in the system. So the magnons don't know where to go. Yeah, we offer the magnons an alternative. Why don't you go into the Bose-Einstein condensate? And Andre and his people have shown that indeed this happens. So we can get Bose-Einstein condensation. So we are not even better than the atomic community who has to go to nanokelvin. We are also much better than many people in our own community who need a lot of microwave equipment. We can do Bose-Einstein condensation in our own kitchen at home. All we need to have is just an oven, yeah, to heat it up, and some kind of equipment to detect the Bose-Einstein condensate magnons. So maybe a simple MMR system would already be sufficient.
And to cool down within nanoseconds.
Yes, we have to cool down in nanoseconds. I will, later on, somewhat later, I will address it, how this is done. But that is not the most difficult part. And there are more ways. One is the spin-Seebeck effect and the spin-Hall effect, spin transfer torque effects. These are just names of effects which are able to bring in magnons into the system or to take out magnons of the system. So there are many ways, and I'm sure there is even more ways how to do it. So let me now focus here on this one, just as a best example. So what do? We have precessing moments, but I have to stop this here. No, let's just let it run. What happens is that the precession typically is not a circle, but it is elliptical. Yeah? Why is that? Why is that? It's very simple. This here again is a piece of YIG, yeah, a thin film, yeah. It's only a micrometer, as you see, yeah. And now we have magnetic moments, and the magnetic moments are like this. It's in-plane magnetized, and now the moments precess, and they would like to precess in a circle, yeah. But you will immediately realize this is very expensive, because if I take a snapshot at this point of view, you see it points out of the plane. So we have the demagnetizing fields. Yeah, and they cost a lot of energy. If it is just here in the process, it's fine because it's in the plane. But here again, it has a component pointing to the bottom, so it doesn't work. So what is the system doing? Of course, physics is always finding a good solution. So the system decides not to precess with a circular shape, but to precess like this with an ellipse. Yeah, okay. So that the out-of-plane component is kept at a minimum. Yeah. This has, of course, a different frequency. There is more energy in the system because we have to overcome this field. And you just have seen it here in this animation. Yeah, you see it. I mean, if you now look from the top and if you think that it's just a spin like you have seen, you see the elliptical behavior. And also what you see is that the distance here from the moment to the center is larger here than it was here. So if you describe it now with your usual mathematical tools, take a Fourier transform of the movement, you will find that overtones are appearing, yeah? Because it's not a circular movement anymore. In order to compose this elliptical thing, you have to take the ground tone and the overtones, yeah? Or the harmonics. You know. So you get harmonics into the system. And this can be used. For instance, what we can do, we can bring our system. So here is our film. That is here, this film. We can bring it into a microwave oven, so to speak. Yeah, we better use good microwave equipment. And what we do is we do pumping right here. Yeah, and then each magnon. I now like to change again the scenario. I'm going from spin waves back to magnons. So each magnon will decay into two other magnons, 3-magnon process, first nonlinearity. And each of the new magnons have only half the energy available, so roughly. Yeah? And then we can look for what will happen. They will be somewhere here on this line. Actually, they will go to this state and to this state, even farther out. So the magnons are there. So we pump these states, so we fill the dispersion here exactly at these conditions, somewhere here along the dashed line. So most likely it will go here and there and there. So everywhere where the blue curve just crosses this dashed line, which indicates half the pumping frequency. So we fill the states. And then what happens, this 4-magnon scattering sets in. 4-magnon scattering is always allowed. So you see 2 magnons from here will scatter into other magnons, and this happens on and on and on and on. It's a very incoherent process. So we fill the entire area here with magnons. And what will finally happen is that the magnons want to go somewhere, and you know a system always wants to go to the lowest energy state. And what will happen, the lowest energy state is just the minimum here, what you find here. And in this way, Bose-Einstein condensation is formed. And there's nothing else, only in different words, what I was telling you before. We increase the number of magnons here in this scenario above thermal equilibrium. Yeah? And these excess magnons provides then the number. If you calculate it, you don't need so many magnons. There's only 4% or so of the thermal population. That is already sufficient to trigger Bose-Einstein condensation at room temperature. And then again, you see how different things sometimes are. 4% doesn't sound very much, yeah. But in terms of Einstein and the ultra-cold gases, yeah, this is a huge amount compared to those scenarios. Just compare different scenarios. So that is how a Bose-Einstein condensation can be formed, and that is a way which is very, very often used. Here again, it's shown what happens. We have the three magnon scattering process. We now do Brillouin light scattering, and what we do is just we measure here in a certain frequency window, and then we can move the frequency window across the entire dispersion, and then we get here the spectra. We have a wave vector uncertainty, which is an intrinsic feature of BLS. We never have absolutely sharp wave vectors, but we can manipulate it. We can have it much narrower window, but the price is always measurement time. So we like to work with some uncertainty in order to get some experiments done. And the process of Brillouin light scattering, I think you are very familiar, is inelastic scattering of light. Incoming laser photon scatters from a magnon, and the photon which is scattered carries away the energy and the momentum of the magnon, and this shows up at sidebands in our Brillouin light scattering spectra. Good. So, and now what we did new is we developed a setup where also we have wave vector resolution, very good wave vector resolution, and then we can measure it. There are many ways how to do it. We can work with metallic or dielectric mirrors, which makes the wave vector larger. Let me skip this part here. And here you see a nice setup. And do you have it by now on your left too, the wave vector resolved BLS? Okay, next proposal. For instance, that was a clever guy, Dima Boschko, also part of the Ukraine community. He is now in Colorado Springs. He develops this setup where basically you can change the light angle of incidence. What matters is the projection onto the sampled surface. That is a relevant wave vector, and you see that the projection changes with the angle. So with this nice experimental technique, one can very nicely see and get another wave vector effect. And then it can be extended to time resolution. I don't go with you through the picture. Essentially, is you put some microwave pulse on your sample, you create a Bose-Einstein condensate, and then with time delay, you monitor what is happening and how it is developing. And I will show you some data. Here again, you see the dispersion. Just to remember, backward volume mode, negative slope, minimum. And all these blue lines here are all the thickness modes you have seen at the very beginning, which always exist. Basically, they are usually very close to each other. You can regard it as a continuum of modes, which is very practical for our way of thinking. And we will pump here at a certain frequency, FP, which means a pumping frequency. The pumping frequency is somewhere here, and half the pumping frequency is here, and that is where this, in the parametric process, the magnons are excited, which then further on decay. So I turn it around, and now we can do an experiment, Brillouin light scattering. We now measure as a function of wave vector, the wave vector resolved BLS, not frequency, as a function of time, with time resolution. And then we see, here we do strong pumping, so nothing really happens. Here in the window we are observing. And then we see that here now, if we switch it off, that here a magnon gas is formed. All this bluish area is a magnon gas. And then if we wait a little bit, we notice that many of the magnons from the magnon gas makes their way into the Bose-Einstein condensate, which shows up here at this reddish part. That is original data. Yeah? If we do large pumping, then you see here pumping is very, very strong, pumping power 25 watts. And what happens here in this case is during the pumping process, nothing really happens. It's very interesting to calculate the temperature, which we can do with simple thermodynamics. It's 30,000 Kelvin. So our condensates are not colder than everything else, but even hotter than everything else, hotter than the surface of the sun. Yeah, so that is in our lab. Yeah, but we don't burn our fingers because the coupling is so weak. Yeah, there is an intrinsic problem of magnonics, and we have to develop strategies to overcome it. But now, if we have this very, very highly pumped stuff, and if we now wait that after switching off the pumping, again, a condensate is formed here. Yeah. And that is actually the usual scenario which we use. Yeah. Let me switch that. Okay, is it a condensate? You can ask questions here. Number one is, I was somewhat cheating to you, because I was always calling it a Bose-Einstein condensate, assuming a Bose-Einstein distribution function. And now I have to confess it was somehow cheating, because I was implying we are living in a quantum mechanical world. The cheating is it's not a quantum mechanical world. It's still a classical world. It's Bose-Einstein condensation in a classical world. But I must say, everybody uses this terminology, but one should be aware that this is the case. Yeah. But isn't it nice and useful that we can use our entire instrumentarium of quantum mechanics to understand this very complicated classical world? If any of you would have been sent home for an examination to describe these processes in classical terms, only Maxwell equation and so on, you would die. You would die. It's possible, but you would die. Maybe nowadays with ChatGPT, but the poor professor who has to check whether your calculations are right is really in a bad shape. But we have a few statements. Actually, yes, I should make this comment. Quantum mechanics has one big disadvantage for you in the lab, and that is you cannot probe a quantum mechanical state. You cannot measure it. As soon as you try to measure a quantum mechanical state, you are destroying it, or in another language, your measurement process becomes part of your quantum mechanical system, and in this way, you are manipulating your quantum mechanical system. But in classical world, we are so much used that we have a system, we are looking on it from outside, and we are measuring the system. Yeah? Even the word, we are measuring a system, is totally wrong in a quantum mechanical environment. But in a classical environment, we are doing it. Yeah? Andre is measuring a magnonic system because he throws photons, light photons in the system, in this BLS system. Yeah? He still uses, well, you all from the group, you're using the wrong terminology. Yeah? You are not measuring a system. You are interfering with the system. So, but what can be done? There are ways out. And one way is just to combine quantum mechanical systems with classical systems, so to give them a classical component, because then you can measure the classical component. If you are fully aware what you are doing, you can even infer quantum mechanical properties in a better way. It's a tricky business, yeah, because it only works for multi-particle systems where one component still stays multi-quantum. You must have things like entanglement. Next question is, what is entanglement in a classical world? Very difficult. Yeah, there is an analogon, not the same thing in the classical world, but this leads too far now. But what we can do is we can ask questions. And one question is it really a BEC? What is the condition for a BEC? And BEC is given if the order parameter is coherency. So we have to show that coherency is acting here, and the phase should be undetermined. Yeah, if we form a BEC condensate, and it is really an ordering process, we can tell nothing about the phase. But what we can do, we can measure the phase in a classical system. Yeah, and if we measure the phase and find out that the phase is random, then I think we are there. And I will now show you how we do it, and that is very recent work. Yeah. Definition of coherency by David Snow as spontaneous coherence is so essential to the phenomenon of Bose-Einstein condensation. To prove that one has a condensate, one must demonstrate two things. First, that there is coherence, and second, that this coherence is spontaneous. So it's not predicted by some mechanism. So, well, we went there, and we did this. And this is now the highlight, so to speak, of my lecture today, the scientific highlight. let's just repeat a little bit just to get you more trained. We measure the Magnon density with our BLS or some other means as a function of frequency. And if we pump our system, we get this blue distribution curve. We get a peak here at a frequency. If we do an analysis, yes, there is a frequency where the parametric pumping is happening, where we are throwing the magnons into the system. We see some distribution because these magnons will immediately decay into other magnons, forming the magnon gas. The magnon gas will have some kind of distribution. If you take all the details into account, you will find this here. You get magnons above and below, and so on and so on. Yeah. You cannot quantitatively well understand it. If you do a very highly sophisticated numerical simulation, you will get it. But now, if we wait and do the same measurements, these are measurements, yeah, what we will see this very sharp BEC peak, or we call it the BEC peak. Yeah. We also see some background you see here, yeah? And that is just the remaining magnon gas, which you have in any BEC scenario, even with ultra-cold atoms. Yeah, not all atoms make it into the condensate. You still have many atoms around which are not part of the condensate. So we see very nicely all these features. So, but we can bring it on the computer. A computer is so often so helpful because the computer can help us to avoid measurement time. It can steer us in the right direction, and so we only have to do the key experiment in a real experiment. And other experiments, we can just simply ask the computer. So the computer is guided, yeah, Norbert?
But the question is, how good is the model? What is you make the simulation based on
Yeah, these are software packages, MUMAS 3, and they have the Landau-Lifshitz equation in it. They have also the demagnetizing effect. Everything is in it. Very time-consuming. Yeah.
So you really, the core is Landau-Lifshitz equation solved numerically.
Yeah. On a grid. Yeah. Mm-hmm. On a grid. And you see, if I say on a grid, you see already the difficulties, how to choose a grid size small enough that you get the details, but the calculation time is not diverging. Yeah. Okay, so this is a numerical simulation with MUMAX 3. And you see, we find very nicely here, we see the dispersion. You can see probably only in the first row, still the backward volume mode here, and then we get a lot of population here. And then we see again the quadratic increase here for higher wave vectors, and here's the BEC is formed. Yeah? Is it a BEC? In a computer experiment, we can do a very, very simple trick. That is simply by not bringing these two BEC to interference. Yeah? They should be coherent. We don't know the phase, but they should be coherent. And then here's a coherence picture. Yeah? And now our friends from superconductivity come along and said, okay, we know this from superconductivity. We also get coherence of our superconducting states, but you should find something very special. These are vortices. Yeah, such a system should bear vortices. But if you look very carefully, you have the vortices. So here is one, there is one. You see some lines here, some interference lines, which stop here in this area. So every detail is there, what you would expect. Yeah? And it all comes only from the Landau-Lifshitz. It's all contained in the Landau-Lifshitz equation of motion. The most influential paper to me when we were coming into this field was a paper from a dear friend in theoretical physics who unfortunately died a year ago, Gerd Schön. Gerd Schön was in superconductivity. You probably know him. Yeah. And Gerd Schön wrote a paper, actually in German language, for the Physique Journal 20 years ago, where he showed that the Josephson effect can be treated as a classical effect. You don't need quantum mechanics to understand the Josephson effect. You need quantum mechanics to make the Cooper pairs or to make the wave function. But once you have the wave function, all the remaining part of the theory of the Josephson effect is classical physics. And that helped me a lot because it made me confident that what we are doing here, we are doing classical physics, is really the right way to go. And you see the result. Okay, now coherency.
Can I just ask a question?
Yeah, sure.
I did not get the point you said. The coherence need to be spontaneous, cannot be predicted by anything. I don't get that point. Cannot be predicted by anything.
Yes, just the following. Yeah, of course. You do an experiment, you make a BEC condensate. You don't know what the phase is because the phase is spontaneous.
It's a random phase distribution.
It's a random phase distribution, yeah. I mean, in fact, what we do it in a stroboscopic way, the experiments. So we make condensate every millisecond, yeah, and then we can average, but the average phase should just be arbitrary.
And how do you give the proof for that?
I will go to show you.
Are you?
That is exactly the next few ULABs, yeah. So what we need is high-frequency resolved microwave detection of Magnon BC Brillouin. Brillouin is coming to a limit because we don't have good enough resolution. So what we can do here is simply we can switch. It skips this. We will switch to electromagnetic detection, so just using microwave equipment. So you have all the equipment here to do the same thing, because microwave equipment has a fantastic frequency resolution. But we cannot work with microwave equipment at finite wave vectors. That is a big disadvantage, unless you play some tricks. Yeah, but usually it's not possible. So it is difficult to probe farther on these bottom states where the BEC is forming by electric measurements, because the wavelength is usually too small. You cannot make such small antennas and so on. So you are running into a lot of problems. There's only one solution to these problems, that is to have clever people who come up with good ideas how it can be done, and that was done in my lab. So we were not working with a film anymore. We were working with a cuboid. So this is a film. This is a cuboid because it has a finite thickness. Yeah? You know, such a thing you do normally not want to have in magnetism, because you don't know how to treat it. You have so complicated demagnetizing fields. You have even edges and corners. We have divergences. If you try to calculate simple-minded dipolar stuff, but already here you are coming to a limit. You cannot do it analytically anymore. Yeah, but if you have such difficult scenario, I am always advertising. Don't think about the difficulty. Think about the richness behind the problem. Yeah? So use it for something. And the richness is shown here. For instance, if I have such a cuboid, and if I plot along this line the internal field, yeah, the magnetic field, it looks like this. It has a maximum value defined by external field, anisotropy, name it, yeah, which is just here, but at the corners.
Now I would address a few features regarding the coherence. And the new tool which we have available is that we can use high-frequency resolved microwave detection of a Magnon BEC. And that is new. Let's see. Entschuldigung, sorry, I just need to do it again because I forgot to switch on the laser pointer. So let me start again. So next cut. Now we would like to address coherence. Korrektur, ich fange nochmal, I will start again. Cut. Now, a very big issue of a Bose-Einstein condensate is, of course, coherence. We need an experimental technique which can directly prove coherence. So far, we have only assumed that coherence is present in a BEC. Once again, I need to start again. Sorry. If we discuss, I can't find a good start. Now again, cut. So far, we have discussed condensation into a Bose-Einstein condensate of magnons. We assume that coherence plays a role because the degree of coherence is just the order parameter in the BEC process. What we would need to do experimentally is to prove directly that coherence is present, and in particular how coherence is developing. So let me show you now a series of experiments where we have exactly done so. I will report how high-frequency resolved microwave detection of a Magnon BEC can be used for that, and that is a new experimental technique. So far, as I was mentioning before, we were using Brillouin light scattering spectroscopy, and that is a fantastic technique because we have a very high sensitivity and we have frequency as well as wave vectors, space and time resolution available. There are some disadvantages which come along. One is that we have a low frequency resolution, which never can go below 50 or 100 megahertz. And also another aspect is if we think about future devices in any kind of applications, Brillouin light scattering is not really suitable for practical applications. If we would like to think of lines, we would need to a pure electrical detection. So how can we detect the electromagnetic radiation? So, and with equipment, we can achieve a very high frequency resolution, and that is necessary to resolve the single state signal at the bottom of the BEC spectrum. And we might use that for direct display of the BEC coherency. And I will show you how this works. It was clear what I said before, that this could also be important for applications. And if you would like to integrate any kind of magnonic BEC state into electronic circuitry. So, however, there is a difficulty. And the difficulty is simply that if we look into a BEC state, as we have seen so far, these bottom states are hard to detect because the wavelength is small, only a few micrometers. And with electromagnetic detections, this means of antenna structures and microwave equipment, this is hard to achieve. However, we can play a trick, and let me show you the trick on the next view graph. That is simply, if we now use a cuboid, then we know that at the edges of a cuboid, you see here an edge and you see there an edge, we have the demagnetizing fields. And so the internal field varies, and correspondingly also the wavelengths. You see it very nicely here in this animation. If we look into a spectrum, here is a spectrum, and here is the wave number, then we know that the wave number, the spectrum looks like this. We have the minimum point where the BEC happens. We see all the standing waves, and if we measure a spectrum, we see all the bulk modes which we might find in a spectrum. However, at the edges, the internal field goes down, and an external field which goes down basically means that the dispersion curve would shift downwards. You see it very nicely here in this animation. So if we go here from the center of the cuboid to the edge where the field is lower, the corresponding dispersion curve would shift down. And that simply means that if we measure at a certain frequency, we probe different states as we move the position of the testing here to the edge. Of course, in a real experiment, we average over all the states. So if BEC happens, then we would find it here at this point, and we could then detect it here at a wavelength, which is now very, very large, because you see the BEC state moves over here to the edge, and here the wave number becomes 0. This means the wavelength becomes very, very large. So that could be a good way how to detect these kind of states. So let's see in the next view graph whether it works indeed. And in order to do so, we use a cuboid. Here you see this little cuboid made out of YIG. There is a loop around it, and this loop is connected to a vector network analyzer. And so we can measure the system. We excite the system with a microwave generator, an amplifier, an attenuator, the usual stuff. And we use here a dielectric resonator about it, just to see to achieve suitable fields, electric field strengths inside our magnetic field strengths into our system. So the sample here is a cuboid 300 by 300 by 600 micrometer. Pumping is done using pulse microwave magnetic fields inside the electric resonator. The pumping part is always shown here in orange. The BEC detection is done with a spectrum analyzer and an amplifier, so via an inductive loop antenna around the sample, and the frequency and intensity measurements of the Magnon radiation spectra is then analyzed by the spectrum analyzer. This all works with time resolution, and we can now see what the experiment provides. So a typical spectrum you see here, you see the frequency here, and you see resonance modes. These are the bulk Magnon modes, which you always find in such a system, and they are discrete because of the small dimensions. Now, if we do the bumping, at the very beginning, during the bumping, we see here all the edge modes up to the minimum frequency, and here we see the discrete bulk mode spectrum as we have seen here in the absorption spectrum. Now, if we move on, if we wait a little bit, so half a microsecond later, you'll see here that in the spectrum of all these edge modes, already some narrowing takes place. And if we wait a little bit longer, then you see how nicely how the system now develops. And 2 microseconds later, we see a very sharp peak at the position of the Bose-Einstein condensation. That is above the condensation threshold. If we do it below the condensation threshold, just by pumping at much smaller power, then you see that nothing seriously here happens. So can we measure the coherence in the system? So let's see. For this, let's choose a different geometry for better access to the BEC via these electromagnetic measurements. So we now use a YIG sample again, but we now apply the external field perpendicular. Then we find a dispersion behavior, which you see here with the n equals 0 mode. So this is now the forward volume mode in this geometry. And you see also all the standing spin wave modes here with this gray and black and the other lines. You see the minimum state is achieved just right here. And now what we do, this out-of-plane magnetized YIG film, we do parametric pumping. The parametric magnons are excited here at this frequency, at half the pumping frequency. And then we use the conventional for magnon scattering mechanism so that these magnons can diffuse into the minimum and accumulate here at the minimum. And that minimum happens at a 0 wave number because of the perpendicular arrangement of the external field. So here is where we should achieve the Bose-Einstein condensate. Let's look into the experiment, and if we do so, here again it shows frequency as a function of time. Here are the parametrically pumped magnons. We cannot see them because they exist at wavelength not accessible in this experiment. And then we see how the BEC is formed. The effect that the frequency goes down here a little bit has to do that in the initial stage we have generated so many magnons that the saturation magnetization is reduced. So that is a well-known effect, but you see very nicely how a BEC is formed here. Once again, the setup, we do the pumping here in this case with a microwave generator, a switch so that we can do time resolved measurements. It goes via this stub here to the sample. Here you see the sample between the poles of the electromagnet, and you notice that the field is now applied perpendicular to the sample. And then with the Y circulator, we detect here in this blue part the spectrum measured with the spectrum analyzer. Good. So let's continue. So if we look into the last 100 nanosecond of a 1 microsecond long pumping pulse, we see here at the bottom of the Magnon spectrum that we get a nice Magnon spectrum. The parametric magnons would be here, but as I was mentioning, we cannot see them. And now if we wait for the first 100 nanosecond, we see at the bottom already some magnons showing up. And if we now wait for longer, then you see here very nicely how now the BEC is formed. And at the very end, if you get a very sharp peak here. So what about the phase? Well, you know that if you measure waves, we can, with the help of an external reference source, we can measure the phase. So for instance, what we can do if we have a sample here, we can pump, and then we can use an oscilloscope or a analyzer to measure the system. So what happens here is essentially we have the YIG stripe perpendicularly magnetized. We have all the processing moments. A pump pulse comes in. We populate the states. and we measure the signal which goes out, which is induced by the processing moments, an electric signal which is produced by the processing moments. So we have this scenario, pumping happens here, then we have the two parametric magnons being here and there, 4 magnon scattering in between, and a condensate is eventually formed here at the bottom of the spectrum. So these are single shot measurements. They are fast because these are multiple measurements per second. We have a very high frequency resolution, which typically for such a system with oscilloscopes and spectrum analyzers is below 1 megahertz, and measure it with phase sensitivity. However, the disadvantage is no spatial resolution, and it is only sensitive for K near very, very close to 0, because otherwise we cannot pick up a signal with this kind of antenna structure. We can only pick up magnons with a wavelength comparable to the width of the antenna line here. So, okay, let's see what happens. Again, here we switch the pumping on, and here's the pumping off. So this is the time scale. We can measure, of course, the voltages, and therefore you'll find a U here as a measurement of the voltage. And then we see how here something happens in the spectrum. We can analyze the frequency, and this is the data you have already seen before. What we now can do is we can calculate the autocorrelation over a shifting window. And this is just the following. We have a window shown here in green. We measure the autocorrelation between all these many modes which you see here in the spectrum. And if you do that, what you find is its very best is an autocorrelation, which is shown here by this orange line, if you have an absolutely coherent signal. So this means if the signal is absolutely coherent, with 100% coherency, we would expect just this kind of triangular shaped signal. If we measure the autocorrelation here during the pumping where everything is incoherent, what do we see? Essentially only noise. Of course, we see a self-correlation peak always here at the center, very, very sharp, just the experimental resolution. But there's nothing here in between. Now, let's see what we can do. If we now do the pumping, after some pumping, of course, some condensation happens already during the pumping process. And you notice that some intensity is already developing here in the autocorrelation curve. If we continue, then you see here some more peaks appear. And then suddenly here, after switching off of the pumping, the condensate is formed, and we see here a very, very strong autocorrelation curve. So the measured curves approaches very well here the ideal curve, which you would find if we would have 100% correlation. Mind that this is a very nice proof that we have a coherent BEC here present. We can also see the results of the Magnon gas behind, and that is just the deviation between the blue and the orange curve, what you see here. So if we do it as a function of time, then you see here in a summary what the result is. So nothing, no autocorrelation during the pumping, beginning of the pumping, then in the process of pumping, some autocorrelation happens. Here's the transition regime, and after switching off of the pumping, we see that we have a very strong autocorrelation signal now after the condensate has been formed. Can measure it, you see the data here again, which you have seen before. We can measure the coherence value, which is just the ratio of the area under this blue line over the area of this orange line, the ideal case. And then we find here coherence values in the range of 75%, which is very, very good. There are some oscillations here, but this is noise of the experiment. I wouldn't give it a special importance. So I think that is a very good indication that indeed that coherency is there, and we can find a measure of the coherency here in this case. But now let's see what we can do regarding the exact phase coherency. Again, you see the picture here again. We do the pumping. The population is enhanced. And then here we find for all different kinds of modes here what happens. We can now measure the phase. And if we now measure the signal, the real part of the signal, we get these kind of oscillations. We can determine the phase. Let me go back. But if we measure the phase and extract the phase, you see this kind of star-like picture. You cannot identify any pattern here in the system. If we now move close to the end of the bumping, you can see now that for different modes here, obviously a phase is developing. You see it that the phase as a function of time is propagating as it should be, because we have precessing moments. So these moments which precess, they of course, let me try to show this here in this little picture. They of course have a progressing phase, so the phase is constantly increasing. If we go here, now you see that the phase indeed moves very, very nicely. So a well-developed phase here in our system. Now what we can do, we do, of course, a multi-shot experiment. So we average over many of these shots. And then for each shot, we can measure the phase. And then we can do this kind of histogram, what you see here. And what we find is that we find a fairly isotropic distribution of the phases. And in my view, that is the best example of what happens here. BEC is a phase transition by which the coherency is the order parameter, but there is nothing in the system which predetermines the phase. The phase is just adopted spontaneously. And if we do many of these experiments, we notice that each time the phase is indeed arbitrary. And if we average, we get this kind of circular behavior in the phase. In my view, that is the best demonstration what is really going on here. So the coherency is truly spontaneous because there is no predefined phase in the system. So what did we find? So we find that the Magnon BEC is macroscopic, is spontaneously coherent occupation of the ground state, and it is formed out of a thermal, which means incoherent bars of magnons. So once again, how do we find it? It is macroscopic because we measure over a stripe here. So it is quite a macroscopic averaging which we do. It is coherent. That is a measurement you have seen here before. And it is spontaneously because the phase is not predetermined here in our system. Good, so we know that the BEC indeed fulfills all the conditions we would expect for a Bose-Einstein condensation process. Let me now show you that there are several ways how to create it. You have seen already the method which we are propagating, that is via parametric pumping, but there are other ways. And one way goes back to our host, Andrei Chumak, because he and his colleagues have shown that you can also create Magnon BECs via rapid sample cooling. And let me show what I mean. The key idea behind this is that we rapidly decrease the phonon temperature. For a given temperature, we have a distribution of magnons, but we can change the phonon temperature much faster than the magnon temperature. And this simply means if we cool the system rapidly down, we have an excess of magnons due to the imbalance between the phonon and the magnon temperatures. Let's look into the underlying fundamental equations of Bose-Einstein distribution functions. What you have here in G as a function of the energy is just the density of available states, and N here is the density of occupied states. And in order to get the density of occupied states, we have to multiply the density of the available states with this Bose factor, which you find here. And what enters here is the temperature, and what enters here is also the chemical potential mu. Now, in equilibrium, the chemical potential is 0, and we would find a distribution function which looks like this black curve. Shown is here the logarithm of the Magnon of density of the occupied states n, so this parameter here, as a function of the frequency, and you can identify the minimum frequency where the Bose-Einstein condensation is supposed to take place if we create a BEC. However, excuse me, in thermal equilibrium, there is no chemical potential, so this parameter is 0, and if we plot this curve, we get this black curve in a log-log plot too. So now let's assume that the chemical potential, that we heat the system to a higher temperature, then this curve would shift up here a little bit, and the difference in temperature just creates more magnons, which you would find here in between. So what happens now if the Magnon sample is cooled down? Well, let's see the time scales. The cooling rate is now supposed to be larger than the relaxation rate of the low energy magnons. So what will happen is we assume we can instantly switch down the phonon temperature here at a certain point in time from a temperature T2 to T1. So this means we have to get rid of these excess magnons, because in thermal equilibrium, the T1 distribution function is the black line and the T2 distribution function is this red line. So what will happen? First of all, we have viscous Gilbert damping, and this is more effective for higher frequencies. So this means all these magnons will shift down. The underlying processes are two. One is classical for Magnon scattering. You have said many times in my presentation. And of course, you also have Cherenkov scattering of magnons on phonons. So this will also happen, and this will move down here the frequencies. So if that happens, what happens is you see a movement now of magnons here to a lower frequency area, and this will move up. And eventually we can describe the system now with a distribution function where the chemical potential equals the minimum frequency of the system. Let's go back to the graph before so that you see what happens in this case. If the chemical potential equals the minimum frequency, this part here becomes 0. We have the exponential function to the power of 0, which is unity. Unity minus unity means 0. So we divide the density of available state by 0 in a mathematical sense. This leads to a divergence, and this divergence is just a fingerprint here in this equation of a Bose-Einstein condensate. So what do we see? We see the divergence, and that is just here this green line which diverges here at the minimum frequency. As easy as that. So how can we achieve sufficiently fast cooling? The answer here, which Andre found, is going to the microscale. And he and his colleague fabricated the sample. You see here a Higgs stripe. You see here some contacts. These are titanium gold contact pads made out of platinum. And they use that in order to put a current here. The sample is also covered with a platinum layer. They put a DC current through the system, and in this way they can heat. This is the Higgs stripe that you see here. This all is prepared on a GGG substrate. The good message here is that GGG has a very good thermal conductivity. So if they now switch off the current, the Higgs stripe here will rapidly cool down because of the extremely good thermal contact to a GGG, which has a very high thermal conductivity. And this goes faster than just Magnon decay time. The experiment here is done with the usual Brillouin light scattering spectroscopy setup. So a laser beam is focused here onto the sample, and then a Fabry-Perot interferometer is used to measure the system. Well, let's just see what happens. He measures the temperature as a function of time. We can do it with electrical measurements, just measuring the resistivity. We can also simulate it with a simple COMSOL simulation. And you see if we switch on electricity, the current, then the system will just heat up from 300 to 450 Kelvin. And then if we switch off, it will just rapidly cool down. So what happens behind is we use Brillouin light scattering to measure it. And let's see now into the results. Here is a spectrum, a Brillouin light scattering spectrum. You see here the fundamental mode and the first spin waves. And now we apply a current pulse here over a certain period of time. So we do the heating, and what you see is in the heating, the frequencies go slightly down. That is simply because the saturation magnetization will be slightly reduced when we heat the system. So, but now what happens if we switch it off? Well, you see immediately a Bose-Einstein condensation is found, identified here in the data by a very high intensity. Is a color code scheme here, so the intensity just gets up by more than a factor of 10. You see it here on the scale. So we have a condensate here due to fast non-adiabatic cooling and BEC formation. So here is a BEC. We can determine actually the chemical potential from the relative occupation of here the fundamental mode and of the first standing spin wave, which you see here with this very simple equation, what you find here. So the chemical potential is nothing else than just the difference of the ratios of the occupation multiplied, weighted with the frequencies divided by just the sum of the occupations. And if we do so, we find something very interesting. So in red, you see the chemical potential obtained via this method. And exactly here at the position where in the spectrum we find the BEC, we notice that the chemical potential becomes equal to the frequency of the fundamental mode. So just this difference in the denominator of the Bose-Einstein function can be proven here experimentally that indeed the chemical potential equals the minimum frequency. There are many other ways how it can be done. We can control the BEC condensation process by the spin Hall effect and by spin torque effects. Let me show you very shortly the results. The idea is very simple. We inject or annihilate magnons during the DC pulse application. And we can modify the threshold change of rapid cooling. How is this done? Again, we use YIG, we use titanium gold contact pads for the system. We have, in this case here 2 contacts. We can measure the Magnon population here in between by focusing light in a Brillouin light scattering experiment onto the YIG stripe. Here, this is 34 nanometer thick YIG stripes, 2 micrometer wide. We have put platinum pads on top, and the area which we heat is 2 by 2 micrometers. Everything is very, very small, and we use space and time without Brillouin light scattering. So if we decrease the YIG thickness, this means that now the spin transfer torque is increased, and in sputter deposited platinum, we can increase the spin Hall angle. So let's see what happens. Number one is, of course, we can inject magnons if we put a current here through this device. So we have 2 effects now. Of course, the heating we have seen before, but at the same time, we can inject magnons because of the direct interaction between the current and the magnonic system because of the spin transfer torque effect. If that is correct, then we should also be able to annihilate magnons by simply reversing the current direction, what you see here. Same geometry as above, same field direction, but the current direction is reversed. So we have in both cases, of course, magnon generation via the rapid cooling process, but we also have Magnon injection and Magnon annihilation depending on the current direction. And of course, we can choose another field direction when we just apply the field parallel here to the current direction, then there should be no spin orbit torques contributing to the effect. So let's see how this could be done. So here is the case where we know there is a classical experiment, field applied parallel to the current, so no spin orbit torque. And we have seen already what happens. We apply a current pulse, and if we switch off the current pulse, we get the BEC formation because of the rapid cooling effect. It's a well-known effect you have seen before. But now, what happens if we go to this geometry where we should have Magnon annihilation? Same experiment, same current pulse, but you see nothing happens here now. And now, if we do the other current direction where we should get Magnon injection, then we find that now you see that already during the pumping, Magnon injection leads to large amplitudes of the Magnons in the system. Here again, the BC formation. So we can define from such experiments a supercritical spin orbit torque from these parameters. And you see that spin orbit torque generation of a BC is obviously possible. Also here it is superimposed on the heating effect. So we get enhanced condensation already during the pumping parts. So I'm now at the end of my presentation. Thank you very much for your attention, and bye-bye.